everyone. I wish you a very happy new year. Today we're going to be talking about antiderivatives and integrals. Firstly, what is an antiderivative and what is an integral? An antiderivative is an opposite of a derivative, which is the rate of change. It is the opposite, sorry, yeah, it is the opposite of a derivative in that when you take a derivative of a function, that affects a function in a certain way. An example is that if you take the derivative of x, that becomes 1. Antiderivative basically just reverses that effect. Taking an antiderivative of 1 will provide back that x. Reason why antiderivatives are so useful are because of integrals. Integrals are derived from antiderivatives, and I'd argue that if you don't know antiderivatives, then it's going to be very hard to take integrals, at least for real-ish numbers. Integrals are basically the area of a shape, like a curve. You may be wondering, how is that important? We have areas for squares and triangles and stuff like that. Yes, however, integrals are, though applicable there, aren't used too much when dealing with squares or triangles. They're most useful when dealing with curvy shapes, specifically one which is very much tied to pi, this circle. Anyways, firstly, let's say we want to calculate an antiderivative. For the beginning, we're only going to say that we're trying to calculate an antiderivative for a certain power. For example, x to the second, x to the third, etc. Why did I say x to the second? Let's just be x squared, and x to the third is x cubed. Yeah. Now, let us say we've got the function, say, I'll do x. I won't do 1, which is just x to the 0, since we did that introduction. Now, the idea is, firstly, if you take an antiderivative of a power, the exponent's going to be increased by 1. So I should probably add this. Now, the exponent, as I said, increased by 1, so that is 2. So you might think, hey, we're done. Now we can get on to integrals. Nope, it's not that easy. X squared, I should write it like this, yeah. X squared is close to the antiderivative of x, but it's not exactly the same. To do so, we need to take this exponent too and also divide x by it. Now we are done. Why is this the case? Well, think about what if we're trying to take a derivative. If we take the derivative of, say, if we take the derivative of x squared, we get 2x. If you remember when we did. So, therefore, since I said that everything is inverse, well, yeah. So if we did have x squared, then we aren't going to have x as the input, we're going to have 2x in case of the antiderivative, and that's no good. We want x, just clear, plain, simple x. So to get this, we must divide everything by 2, which naturally leads to x on one side, yay, and on the other side we get x squared by 2. I hope you understand why we did that. However, I'm going to do it just one more time so that you actually understand. Now, x to the 4th. Now, let's say we want to take an antiderivative. Again, power increases by 1, x by 5, but remember, take the new exponent and divide the number by it. And as for the reasoning, it's very similar here. If we take the derivative of pure x to the 5th, we're going to get 5 times x to the 4th, which is okay, but then that means we're going to have 5 times x to the 4 as the input. Again, we want pure x to the 4th. So, to fix that, we divide both sides by 5. Removing the 5 on one side, creating pure x to the 4th. Again, yay. And on the other side, we have x by 5 to the power of 5. And finally, what integrals? How to compute them? Integrals are similar to antiderivatives. However, there's one key difference. Antiderivatives, and I better get into some symbology. Antiderivatives and integrals are written like this, a long S. Okay, this isn't really that clear. Let me try and draw it again. Much better. A long X. This is S. This is how you draw it. And then the format is that you now have your function in it, f of x. F of x is a standard term for function. And then dx. Again, if you'll remember, the true derivative term was d by dx. So it's coming back here, except it is multiplying, which doesn't make sense. But if you think about it, remember, integrals and thereby antiderivatives are the opposite of derivatives. So it would make sense that the dx would just cancel itself out. And this is equal to the antiderivative of the function. Let's say a of x, since it's the antiderivative of the function. Integrals are similar. However, they only constitute part of the function. It's a sort of graph. Let's say that we want to find the integral from a to b. Well, then the format is this of f of x. Now, how do we figure out an integral? Well, it's simple. Firstly, we calculate the values for a and b. So firstly, let us say that as an example, we have x. Now, if we take a at x, the function here is x equals y. Basically, not for y. And I'm going to draw a little bit of a graph here, x-axis, and this is the y-axis. So, here what we're doing is that let's say that, and the graph is sort of like this. And this is the interval from 0 to 1. 0, 1, 1. Ignore my very bad drawing. So, here, A, this is the area. We're trying to find this out. Now, firstly, we're assuming that A is 0 and B is 1. In general, we're going to assume that B is greater than A. Why? Because it's just easier. Now, the function at A is, 0, x equals y. Well, x is equal to 0. A is equal to 0. So here I guess I should really write A. A is currently equal to x at this specific location, which is why it will equal y at this specific location. So basically, y is also 0. Basically, the main point, we get 0. And on the other side, we have b. Now, calculate b at the point. Again, same thing, we're going to get 1. Sorry, not that. We're actually not going to compute by this. We're actually going to compute its antiderivative, which is x squared by 2 again. So, it's going to be 1 because 1 times 2 is just 1 times itself is 1. However, then we're going to divide by 2, so it's 0.5. Again, 0, well, dividing by 2 and squaring it doesn't really affect it at all, so yeah. And finally, we need to subtract, which gives us 0.5, which, as expected, if you use the triangular formula, and notice this is indeed a triangle, you will have, firstly, the base is this 1, and the height is also 1. So base times height divided by 2, that's 1 times 1, 1 squared, divided by 2 is equal to 0.5. And if we want to try for 2, for 0 and 2, then, well, the first term is 0, and the second term is 2. So, yeah, that's the area. So that will be, wait, let me draw a separate graph. So, assuming that for this case, we're going to draw the graph here. So, firstly, it will be 0.5 here. Now, we're going to need to do this throughout the function. So, basically, we're going to evaluate, and in a nutshell, we're just going to draw x squared by 2. So, this is an approximate thing. Now, let's assume that we're now trying to find the integral between 0 and 2. Just extend it a little bit. Again, 2 squared is 4 divided by 2. That is 2, if I'm correct. meaning at the last value, which is 2, it will be equal to 2. Since this is x squared by, since x squared by 2, we're going to extend this curve all the way up to here. And this is the rough-ish graph. Now let's assume that you're starting from 1 instead. Now from this case, we're actually going to start at 0. I probably shouldn't have done it. Oh, well, too late. Okay, so 1 is this point, and 2 is this point. And let's say we want to do the integral here of x. Well, firstly, it's going to start at like 0. So it's going to start at 0.5, since that's the area before. And then finally, it's just going to continue like this up to 2. So there you go. Just like that, we have seen how to compute antiderivatives at least of powers, and also how to compute integrals using them. In the next episode, we'll delve into more how to create antiderivatives, especially for polynomials, and also how to create more integrals using those polynomials, using a few examples. Till then, bye!